Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Welcome to Physics with Beth and Beth. We're on that AP Physics 1 curriculum that we will still be on for a few more units, but we're well over halfway done. We can be feeling good about that. We are on Unit 5, Torque and Rotational Dynamics. We're still on static equilibrium. We wanted to come at you. This is, I think, we had 2 problems on summing torques, and we've had a couple of problems on static equilibrium. This is the 3rd, because it's very important. You're going to see these on your exams, on AP exams, on reviews. So let's make sure we understand these static equilibrium problems. Remember, there are 2 things about static equilibrium problems that we've been talking about. The sum of the forces equals 0 and the sum of the torques equals 0. Why is that? Because force equals mass times acceleration. If it's at rest, acceleration is 0, so sum of the forces equals 0. Angular acceleration here, because sum of the torques is equal to that moment of inertia. Newton's second law for rotational times is sum of the torques equals your moment of inertia times angular acceleration. But if angular acceleration is 0, then sum of the torques is 0. So that's going to be the standard on these. All right, and we always know, hopefully if you've seen the other 2 videos, the first step is to do a free body diagram on this. So let's talk about what this problem is. It's a classic. We have a 15 kilogram sign hanging. This is the little sign. So think of like you're in a cute little downtown area. If you're Texas, Fredericksburg, or somewhere like that, cute little downtown area. And you've got a wire hanging out from the wall and a beam. And the wire is attached to this beam right here. And hanging from the beam is a little sign that tells you the store, the shop's name, or something like that. All right, they're going to tell you that this angle is theta. And in my problem, I told you it was 49 degrees is actually what theta is. So this is not hanging perpendicular or parallel. This sign itself is 15 kilograms, and it's 3 meters from the wall. Okay, and the total beam length is 10 meters. So this total length here is 10 meters. Okay, and that sign's hanging at 3 meters. Here's what they want to know. What's the tension in the wire? Okay, seems easy enough, so let's just get started. All right, first things, free body diagram, and we're going to put what's acting on that beam. Okay, forces acting on the beam. So I'm drawing out this line. First of all, we have tension this way. We know that's force due to tension. All right, we also know that we have this sign that's hanging here, so that's force due to gravity of the sign. And we also have the beam itself has a mass of 10 kilograms. All right, and that's going to be right here in the middle of that. And it's actually less than the sign, so I'm going to make that vector smaller, but it's force due to gravity of the beam. And remember, those force due to gravities are mg. It's going to be mass of the sign times g. That's going to be mass of the beam times g. Okay, now this one, remember this distance from here, the wall, to here is going to be 3 meters, but then it's going to be 5 meters from the wall to the center, because we always put, for force due to gravity of that beam, we're going to put it at center of mass, the whole thing. We're going to just put it all on one dot right there at center of mass. Okay, and that's going to be at 5 meters because the beam's 10. So, perfect. Now, there are 2 more forces that you might not see right away. I'm going to do those with a different color. And they're going to be important because they're going to help us decide where we put our axis of rotation, because step 2 after free body diagram is always pick your axis of rotation. So, and because these things aren't moving, so you can pick it anywhere, right? So, but we're going to be strategic about where we pick it. First of all, there is a x component right here of this tension force. Okay, because this, look, this is northwest. So that means there's a west component, dot, 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 and there's a north component, dot, 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 dot. Now remember, don't ever put your components on a free body diagram. I'm just doing that to show you. There's a north component and a west. Okay, well remember, we said sum of the forces have to equal 0 for this object to be in static equilibrium. Well, that means there's got to be a force. If there's a force going west, there needs to be a force going east. All right? But we don't have a force showing going east. That's because the wall is pushing on the beam east. And remember, it's all forces pushing on the beam. So you have a force here that's called a normal force due to the wall. All right? But it doesn't end there. Not only is the wall pushing east on the beam, it's also, in this case, pushing north as well, because you have two pretty big forces that are down here, that are south, and you've got one force that is north. And when we calculate this, it's going to be pretty small, so you're going to know that this is also pushing a force of the wall, normal force, let me do this, a normal force, because it's a surface, so it's a normal force, and it's a surface of the wall. So we like to put force normal of the wall. All right, so it has an E, so there are two forces here that you might not have seen right away, but the wall is acting on that beam. Okay, so now that we have a free body diagram, we have our tension, we have our force due to gravity of the beam, force due to gravity of the sign, and our two wall forces here. And I'm going to try to take out that, that component, because don't ever put components on your free body diagram. AP board does not like that, nor do your engineering classes, all right? Perfect, now that we've got this, second thing is we're gonna sum the torques, and those summing of the torques equals 0. But before we do step 2, we need to figure out where we're gonna put our axis of rotation. That is technically step 2. Step 2 is figuring out axis of rotation. Step 3 is summing those torques. Okay, I have two forces that I know nothing about. My force due to gravity of the sign, I know because it's M times little g, which I have. Beam, also know that. M of the beam, mass of the beam, times little g, we know that. We're looking for this tension force, so I don't want to put my axis of rotation here, because then R is just 0 and I won't have a tension force in my torque. But if I put axis of rotation here at the wall, I knock out both these forces, because both of these are going through the axis of rotation, which means their R value is 0 in that torque equals R times the force. All right, so that means both of these torques will be 0 because the R is 0. The forces are still there, but the torque, it won't produce torque. It won't produce rotation. Okay, so I'm putting them there because I know nothing about those forces, and now I don't have to worry about them. So that's going to be my axis of rotation right up against the wall at the beam. And that is where you really always should put your forces, your sum of your torques, your axis of rotation, I should say, for the sum of the torques, so you wipe those out. It's a good strategy. All right, now we can solve this thing. I have the sum of my torques is going to be the torque from the force due to gravity of the beam, plus the torque from the force due to gravity of the sign, plus the torque from the tension force, and that's going to equal 0. I'm going to start here. We can start with the beam, since I said the beam axis of rotation is at the end, and we said my force due to gravity will be at 5 meters right at the center of mass. So my R for that is 5. My mass of the beam is 10. And mass is not a force. You got to multiply it by G. Remember the formula, M times G. So it's going to be 9.81. Now before I move on here, I got to figure out if that's positive or negative. I have a force due to gravity. It's pulling on the right side and coming around. That is clockwise, so that's negative. Okay? Now we're moving on to the next force. I have my force due to the sign. It is 3 meters from the end where I chose axis of rotation. So that R value is 3 from where the force is applied physically to the axis of rotation. My mass of my sign is 15 and multiply by 9.81 G, because remember force of the sign is mg. And I got to look at that. That is also, if this is axis of rotation, it's going clockwise. So that's going to be negative. Now I look, I have to have a positive torque now, because remember they're going to equal 0, the total. And sure enough, if I were to pull up on this at this angle, it's going to make this go counterclockwise. So it's positive. My distance is from axis of rotation to where that force is physically applied. That's the whole length of the beam. So that R value is 10. My force of tension, I don't know yet, that's what I'm trying to figure out, equals 0. All right, but we have to look at this. It's not, remember, It's perpendicular force for torque. This is not, if this were perpendicular, it would be straight up. It's not perpendicular. So we have to deal with this theta. All right, so I'm gonna blow this up over here and show you. I have my force tension here and I have theta. I need not the west component of this tension force. I need the north component, because remember we said, hey, this was pointing northwest. I need this north component because it is perpendicular to the beam. All right, if that's sine of 49, if that's 49 degrees, that force of tension in the y is what's perpendicular, and that is opposite, that's sine. So that's going to be sine theta equals my opposite side, which is that force of tension in the y, over my hypotenuse. Sine is opposite over hypotenuse, which is force of tension. That's what this whole thing was, the tension force. Okay? Now I'm going to multiply that, so that means the tension force times sine theta equals that tension force in the y, which is really perpendicular. Okay? So that's going to be Ft sine theta equals 0. Now you're like, oh, but wait, when you did that, you're not, if this is the wall, you're not at 10 meters anymore, the way you drew that up. No. It's where the force is physically applied, and it was attached at the end. All right, so a lot of times my students have messed that up and go, how much should I subtract from 10? Where did it actually get applied? No, it's physically where it's physically applied, which would be the end. Okay, so now I'm gonna add all these over here. So I get 10 times my Ft sine theta, which I said my sine was 49 degrees, equals, I'm gonna add these both over, that's 50 times 9.81. So that's gonna be 50 times 9.81. And then I'm gonna add this over, 15 times 3 is 45. So that's gonna be 45 times 9.81. And then you're gonna divide by 10 and then divide by a sine 49. So I'm gonna add these, divide by 10, divide by sine of 49, and you get a tension force of 123.5 newtons. Maybe we would have made that 124 for 3 sig figs. All right, so hopefully that helps. Again, we're just summing the torques. Here we did not have to sum we did not have to sum forces to equal 0. If we wanted to go back and figure out, I want to know what the normal of the wall was, north, and the normal from the wall east. Now we could actually, now that we know tension force is 123.5, we actually could do that by summing my forces in the x would equal 0 and the sum of my forces in the y equals 0. I would have 2 down in the y and 1 up in the y. I would have 1 west in the y, and I would have 1 east in the y because it would be that force of tension. And we would also have, let me go back to that y vertical direction, we would have 2 down in the y, both of our forces due to gravity. We would have 1 north or up, that force normal of the wall, and we would have another force up from this tension, because remember we said, hey, it's got 2 components. It's got a north component and an east component. So you could go ahead and find both of those. It's rare that they ever ask you to find these normal forces. They mainly want you to realize they're there on a free body diagram, and they want you to recognize that putting your axis of rotation on there, up against the wall, will eliminate both of those from the torque. Because we could put these in the torque, but the R is just going to be 0 because it's on axis of rotation, okay? So that's how you do this. We're summing the torques, but watch that tension is not perpendicular. It's at an angle. That means you have got to find the perpendicular component to that beam, which is sine in this case. All right, thank you for watching. I hope this helps. If you like it, please give us a thumbs up and subscribe to watch more of our videos that are coming at you. Thank you, and happy, if I can get that out, happy physicsing.